Good afternoon, ladies and gentlemen. This is Rick Almeida with you again, and once again, it's my pleasure to introduce my colleague, Dr. Damon Scott. Dr. Scott will be delivering his 6th talk on mathematical logic, and this week's installment is entitled Using Context to Perform Substitutions in the Integral Calculus. So without further ado, Dr. Scott.
Thank you, Mr. Chairman. I thought I'd ad-lib. I don't usually ad-lib at the beginning, but the purpose of this video is, and it will be produced on video, is to help students mostly with their u-subs. Last time I taught the integral calculus, I was seeing several students doing substitutions in a way I never taught. And if they were good, that would work. But I was seeing really weird stuff. And so I don't know where they were getting the weird stuff. I hope with this video, if students are going to videos to learn how to do their u-substitutions, they're getting good material. But let's take a look here on the method of substitution in the integral calculus. The method of substitution is often called the u-sub. It is a standard fixture in a course in the integral calculus. The method of substitution is often a stumbling block for students. It is presented as an array of manipulation of symbols, mostly meaningless, so as to arrive at an antiderivative. It is presented as an elaborate method for doing the chain rule in reverse. Of course, the chain rule itself is often mysterious and a stumbling block for students. Its reverse operation must be even more so. We have a new approach. We present a new way of doing these substitutions. Rather than symbolic manipulation of symbols that are lacking in meaning, we build up a system of doing substitutions where the whole and every part of that whole has meaning. The result is a way of doing substitutions that is mathematically sound and correct at each step, provided you can accept infinitesimals, which have been subject to criticism. We'll find out. For those who have rusted out some, just digress right now, I had a student, what does it mean to rust out? And I had to explain the chemistry about iron and diatomic oxygen dissolved in water and forming iron oxide called rust. So for those who have rusted out some, calculus is that mass of material you once were taught if you ever took a course called calculus. The differential calculus features the derivative, and the differential operator, d dx, is it coming back? It is called differential because of the difference or subtraction in this very famous definition. I'm suppressing declaration of variables and technical hypotheses that the derivative of a function is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. I've taught this a few times. I can rattle that off. The integral calculus features the integral, which comes in two different varieties, the definite integral and the indefinite integral. The definite integral may be effectively defined as follows. Again, I'm suppressing the declaration of variables and the technical hypotheses. Of course, I would include them in a real class I was teaching. The integral from a to b of f of x with respect to x is the limit as n increases without bound. Remember this stuff? Of the summation as I goes from 1 to n of f of a plus I delta x times delta x, where delta x itself is b minus a over n. Perhaps a separate video would do that. It takes an hour-long presentation to explain all that. Far more complicated formulations are given in standard textbooks. I don't know why, because they give the same answer as this formulation given above, which is much simpler, and it works for all continuous and piecewise continuous functions. So, let's move on. The differential calculus is the mathematics of continuous change. That is how I present it. The integral calculus is the mathematics of continuous accumulation. The fundamental theorem of calculus asserts that continuous change and continuous accumulation are reverse operations of one another. For full details, consult your nearest calculus textbook or calculus teacher. The integral calculus thus has a fully self-standing meaning, as fully self-standing a meaning as does the differential calculus. To consider the integral calculus as only the inverse of the differential calculus is to drain almost all meaning from it. Now, let's take a look at the differential as something meaningful. This differential dx once meant an infinitesimal change in x. The notation d, all standing by itself, meant infinitesimal change of whatever you're doing. Thinking in terms of differentials fell out of favor, since they were accused of not being rigorous enough or were inconceivable numbers less than any ordinary positive number and yet not exactly zero. Another little aside, when I was a graduate student, my dissertation advisor tried to get me sold on non-standard analysis, some axiom system, and I could not conceive of these things, and I, for one, do not do inconceivable mathematics. I just don't. So since I could not conceive of it, I did not do non-standard analysis, and my dissertation is, you'll be happy to know, entirely in standard mathematics. If we can loosen up just enough, we can think of dx as an itsy change in x. Consider a situation where du is negative twice dx. Then, when x is 1, each itsy change in x results in negative 2 itsy change of u. I'd like to move over here if I can and show this, if this will show up on the video. It surely shows up for the audience. Here we have u being 9 minus x squared. Surely, if I take the derivative with respect to x of both sides, I get negative 2x. If I formally multiply by dx, I get this. And I've always taught it as formal, that now the symbols don't necessarily mean anything. But let's see if we can confer some meaning. If du, if x is 1, and du is itsy, well, we have negative 2 itsy. So if I change x by 1 itsy, u changes by negative 2 itsies. And you can see it happening. When x is 2, du is negative 4 dx. So for each itsy change in x, oh, look, I'm falling down negative 4 itsies in the u department. If you take a microscope and zoom in on these things, the difference between the graph itself and a straight line becomes less and less. So this is how people thought back in the days of the Bernoulli brothers and the heyday of calculus. That Bishop Berkeley criticized these things as ghosts of departed quantities did not deter these people from doing their thing. And I think it's not bad for us today to at least confer some meaning, even if it can be criticized for these differentials. So, the criticism that can be hurled at the word itsy cannot be more than has been hurled at the word infinitesimal. And so we're just going to proceed. The integral, or the differential in integrals as meaningful, is going to be presented here. The expression, the integral from 0 to 1 of x squared with respect to x, was once conceived in this manner. I'll move over here, see if the camera can follow me. As x goes from 0 to 1, it increases by itsy increments dx. And for dx would be a little, I multiply that little change in x by x squared, which is the height up to this graph, and I get the area of that little sliver. Then if I continue on and accumulate all those slivers of area, I get the area under the curve. This is a way of doing it before, I believe it was Cauchy, say, let's all do this more rigorously with limits, which works. But you can see dx has meaning. I've taught the integral calculus many times. Just getting the students to write the dx can sometimes be a challenge. And why would a student do that if dx has no meaning at all? But you can see that dx is essential to the meaning of the whole expression. And of course, that fancy S means summation. It accumulates for us. So I'll just repeat this. We can accumulate these slivers of area with the integral operator and so arrive at a conception of this integral from 0 to 1 of x squared dx as the area under the curve. Both students and professors can appreciate the more modern definition of the derivative and integral as very special limits. The gain in rigor is very substantial, but something is lost. Thinking in terms of infinitesimals gives meaning not only to the whole, but to every part, even to dx. So we are no longer just pushing meaningless symbols around, but symbols that may well have some meaning to them. My next topic is of relative derivatives. This topic could be covered in a conventional introductory course in calculus, but usually does not for want of time. Technically, it's somewhere embedded in that lecture on the chain rule, which maybe the professor himself, what's going on here with all that? But let's go get this going. We need this topic in order to do substitutions in integrals in a thoroughly sound manner. So an ordinary derivative is of a function with respect to a variable. The derivative of x squared with respect to x is twice x. A relative derivative is of a function with respect to another function. Here's the definition. The derivative of a function f with respect to another function g is the regular old derivative of f over the regular old derivative of g. The dx's appear to cancel, and you're left with that. And some night or whatever, if you have more time on your hands, you may think about ITSEs and ITSE change in x doing this and that, and see that it makes very good sense. We may work through a very simple example, the differential of x cubed with respect to x squared. Well, would be by this definition here, the derivative of x cubed is 3x squared. This is 2x down there. Touch of simplification yields 3/2 x. Just a very simple example. Let me neaten up my table here and move on. The next topic, so that we can get to this, is of relative integrals. Relative integrals can be defined similarly. An ordinary integral is of a function with respect to a variable. For example, the integral, indefinite this time, of x squared with respect to x. A relative integral is of a function with respect to another function, and here's the definition. The derivative of a function g with respect to another function f is, by definition, the integral of g times df dx, like that. Apologies to people who may be blind and only hearing this. You have to see that to make sense. But this is the definition. We can run through a very simple example to integrate x squared with respect to x cubed. We have this. We just take dx cubed dx, and dx, you almost see the dx's cancel. But now we're not going to cancel them. We're going to move forward. And the derivative of x cubed is still 3x squared, I sure hope. And we simplify some and get our answer. And we have our plus c at the end, as we should have for an indefinite integral. Another topic, just to make sure we approach this in a thoroughly sound fashion, is of unity packets. Unity is an old-fashioned name for the number 1. One may multiply any quantity by unity and maintain equality. A unity packet is the product of a non-zero number with its own reciprocal. For example, 1 is 2 times 1/2. 1 is also negative 1/2 times negative 2. There are all sorts of different unity packets you can buy at the store. They give them out just about for free, negative 1/3 times a negative 3, and so forth. Most professors, but not all, will allow times a negative provided that the multiplication is emphatically written out. So we can write this unity packet as 1 being -1/2 times -2. And we can also write 1 as -1/2 times -2 using the old Fortran symbol for multiplication to be even more emphatic about that multiplication. But if I do not write the multiplication symbol, -1/2 minus 2 is still -1/2 minus 2, which is -2.5, not 1. So make sure if you do this to make that your multiplication symbol shows up loud and clear. And now for something completely different. My table of authorities this week is Euclid's Elements. I have here the Dover edition, which I recommend very highly. It is Heath's very famous translation and beautiful commentary. This thing, Green Lion Press, has made a nice hardbound edition of Euclid's Elements, the Heath translation, but without his commentary. And they even published this one, which is just the theorems with none of the proofs. So you can go find what you're looking for quickly. My own opinion is that Euclid should be on every mathematics professor's shelf. That's not my own personal opinion. What is Euclid doing here when I'm talking about the integral calculus? Is it geometry, number theory, theory of different kinds of irrationals, solid geometry? There's an adage. It's not what you say, it's how you say it. Euclid presents his proofs so beautifully well. And Euclid was doing context-oriented mathematical logic before context-oriented mathematical logic was cool. So Euclid will be our style setter as to how to form our mathematics in a beautiful fashion, rigorous and clear. That is what Euclid is doing today in our presentation. So, we'll look at the single most famous theorem of them all in Euclid's Elements, proposition 47, the proof of the Pythagorean theorem. Here's this beautiful diagram, courtesy of David E. Joyce, professor of mathematics and computer science at Clark University. That's just a diagram. The proof, of course, is Euclid. So Euclid says things like this. This is very paraphrased, but means the same thing. Let ABC be a triangle, and suppose that the angle BAC is a right angle. Bit modern notation for that. Those who've been following these presentations in order will recognize that's a context. Part of a well-formed mathematical context, if we wish to rigorize it, that is a context. Oh, here's another context. Let ABFG be a square, BCDE be another square, and AK, where are we? This square also. He creates these squares. We are to show that the areas of the squares add up. Now, he also says this. Let L be the foot of the perpendicular from A to DE. His language was different, but that's what he does. That's another context. This context has a special quality to it. It is called an auxiliary construction that has no motivation to it. Euclid just goes and drops that perpendicular for no apparent reason. You'd have to read the proof to see where the Euclid starts using it. He does not, he will in fact use L midway through the proof. It shows up a little bit late in the argument. But Euclid puts that context here before he begins his first deductive reasoning. And that's excellent, I think. Euclid should be a model for us all. Set up your auxiliary constructions at the top of what you're doing, and they'll pop into use right when you need them in the midst of your argument. And of course, a proof of the Pythagorean theorem is well worth another presentation. I'm sure there are good ones, I should hope, out there. Or you can read Euclid, there is no better. So let's know how to introduce auxiliary constructions. The classic auxiliary construction is the point L in the example just given. To introduce an auxiliary construction, one must confirm three things about it. It must exist. In fact, it must provably exist if you're going to use it in proof. The difference between something existing and provably existing in mathematics, you'd have to go back to the Gödel incompleteness theorems and all that stuff to make the distinction. In mathematics, what we have is generally what we proved to have. So your auxiliary construction must provably exist. It must be given a name that does not clash with any previously defined variable. And it must not appear in the result being proved. If it does appear, it's not an auxiliary variable. Now, is it? After checking these three things, one introduces it with the context, and in English, it is with the use of subjunctive verb let. So that's how we do things. I don't know what it is in Greek. Euclid certainly did, but that's how we do these things in English. So, let's talk some more about these auxiliary constructions. There is no method that works in general for knowing what auxiliary construction should be introduced so as to get a theorem proved, or for us later to get an integral evaluated. In fact, one can work it out as a corollary of Gödel's first incompleteness theorem that there cannot be an all-powerful method that works in complete generality. Even so, many auxiliary constructions are in such well-worn territory that one is not groping at random, but can know what auxiliary construction should be used in that instance. And we'll see that here. The professor of calculus certainly knows what auxiliary construction to do. He's been doing it for years. The student might wonder. So, with all this preparation, let's get to work. The remainder of this presentation is to evaluate this one integral, the integral of x times root 9 minus x squared, with respect to x. Those of you who are math professors, don't shout out the answer. The solution cannot be done by using the product rule for integrals because there is no product rule for integrals, and its counterpart, integration by parts, does not work either. The solution is an exercise in the method of substitution. The solution requires an auxiliary construction, and as I've just said, auxiliary constructions in general are hit or miss affairs. Here, the magic auxiliary construction is to let u be 9 minus x squared. And those who've seen this say, oh yeah, if I do this, that'll work out. No, all that will work out. But until you've seen it, it just is out of the blue or out of the hat. After you have attained some practice, you will learn how to make substitutions on your own. And I repeat, the method of substitution does not always work. So often it simply does not work. It is not an all-powerful method. That's just the nature of the beast. So, how not to do this rigorously? This is painful, because this is how I've taught it all my life. All my life, I've taught students to start with what you're trying to do, set an equal sign, and keep going, and then do a substitution. I teach it as a digression, and so forth. This was before even I had seen these presentations, and I thought, oh, Euclid will show the way. We are moving up in the world. The exposition for this problem will look like a proof in Euclid. So let's see how it works. The student will write what is in black. We find the integral of x root x 9 minus x squared with respect to x full stop, an old-fashioned word for period. Oh, it has English words in it. Do you think by the time a student is in the integral calculus, they could start using English words in their exposition? I hope so. So we state the problem. Let u be 9 minus x squared. We introduce the auxiliary construction. Check it out. Does 9 minus x squared exist? It's a quadratic polynomial. U itself then is a function of x and is in fact a quadratic polynomial. It provably exists. We've given it a name different from any other, and it does not show up in the original problem. It satisfies all the criteria for being an auxiliary construction. We continue on. We take the derivative of this function u with respect to x, and we get negative twice x. And we separate the differentials, and if you are into itsy analysis, you're not losing meaning. It's a little fuzzy, but this is as meaningful a line, or at least it was, as meaningful a line as any other. We launch the main string of equalities. The adverb now introduces a fresh line of deduction. It means you're not deducing something from the line above it, you're starting afresh. That's how we mathematicians use the word now in our expository practice. Look at all this we've done. So we have our problem. We have our unity times something. We break open this unity packet to negative 1/2 times negative 2. Negative 2 is a constant, and constant multiples can hop inside integrals, and multiplication is always commutative. Now, for those first seeing this material, that is just one unmotivated step after another. However, let's see what happens. We have root 9 minus x squared, that's u. And negative twice x dx is du. You can't go to u-land without a differential. The cops will pull you over and say you're driving an integral with no differential. Yes? So you have to have an integral, a differential, to drive your integral in u-land. But we can. We can now create this du here. We have root u. And so we do it. We now perform the substitution, hence the name of the technique. We go to u-land. And in u-land, this all makes perfectly good sense. Now, what I would like to do is just complete it out. We go to u-land. Now, I'll just backtrack. Once you see we have to create du, you know to do this. I'll just complete it out and then make many comments. In u-land, this is easy to integrate. We convert the radical to a power, as is standard. To integrate a fixed power where the variables are the same, you increment the power by 1 and divide by the new power, carrying everything else down, and see when your last integral sign goes away, and we can simplify a bit in u-land. And now in u-land, we go back to x-land. U is still 9 minus x squared. And we see that this equals that which was to be found. I would like to pause now and make several comments. We see here, oh yes, certainly, this equals that, and that equals that, and that equals that, and that equals that, and how can a line that is all x's be equal to a line that's all u's? I tell you truly that this line and that line are not in general equal to one another. If you take this and that and clip it out and send it to the next math professor you encounter, it's not true. You can take any one of these and extract it out and it will work, yes, in general. How is it? It's true in this context. Once we set up that context, then this is equal to that. This is a relative integral, and you may work it out that this line is equal to that, provided you are in this context that u is 9 minus x squared. So that's how we do this. Now, and perhaps again, it's a stumbling block. Professors just blithely assume students will accept this when it's a different kind of deduction they've ever seen from whatever they have seen. Then we go into u-land, and now from u-land we go back to x-land. This context may be used as many times as we like. Early in the argument, late in the argument, middle of the argument, that's what contexts do. Just as Euclid could use that point L anytime in that proof of the Pythagorean theorem, he felt he needed it. So we have this wonderful string of equality, and I think this is very sound. What makes it different from previous authors, even this one professor, is now the substitution is given pride of place at the beginning of the works, and it does resemble a proof of Euclid. Now we can get fancy. Oh, well, we have attained complete and flawless exposition. We can do a check. For as check, if you take the derivative of this, and here's all the symbolic manipulations, you do get the old integrand, which is a check. It also is a separate proof of the same result. You have actually two proofs of the result. One finds the result and proves it at the same time. The other takes the result that was somehow found and proves that it is the correct answer. Now we can use some fancy phrases. Instead of the phrase which was to be found, you can say quod erat inveniendum, if you know some Latin. And you can abbreviate that, QEI, to impress your next math professor and make sure you know what it means, because you may have to explain it to him. He probably has never seen the like. So, doesn't it look good? I think it does. Now, let's see what I have done here. We can change the exposition so as to create a flawless proof. Here's what we just did. With just a bit of changing words, superficial changes, we may now make a proof out of it. Proposition, this thing equals the answer we found. For as proof, let u be 9 minus x squared. Please do not capitalize let here. This is an English, this is an English sentence. Then we have this as, we have the adverb now, which we've to launch a fresh string of argument. Then we come across here. Thus, this equals that which was to be demonstrated. And of course, isn't that impressive? Sure to impress your calculus teacher if you should present an exposition like this for him. And it can be even more impressive if we use a touch of Latin, quod erat demonstrandum, for the end, and the beloved QED. And here it is. It really is now looking like Euclid, even though all the content is the integral calculus. The form is very Euclidean. Thank you. I do take Euclid as a style setter. Thank you, Euclid, for telling us how to have splendid style. Now, I have this other example, very pedagogical. For those students who may be relying on this video to do substitutions, we're going to find a definite integral with the same integrand. So, again, we don't start here and launch a string of equalities. We just say we find this and put a full stop. Same auxiliary construction, let u be 9 minus x squared. As before, du dx is this, and so du is negative twice x dx. We have 2 and 3 here. These are in x land. We need to see what they will become in u land. When x is 3, u will be 0. Everybody see that? When x is 2, u ends up being 5. So we set everything up how x and u are interrelated. And we have all our materials in hand before we launch. And we have it as before. Now our problem equals this, a unity packet. The 2 and the 3 are still holding. Break open the unity packet, move the 2, or the negative 2 inside the integral since it's constant. Collect this over there, and have this. And now we go to u land. Negative 1/2 is itself in all countries. X being 3 is the same as u being 0. X being 2 is the same as u being 5. This is square root of u. And this all turns into DU. A slight joke I tell my classes about these DU things. If you go to another country and you shell out all this money and they give you this one thing back, you might feel like you're being shortchanged, yes? But they are in fact equal. So this is the exchange rate between itsy bitsy changes of x and itsy changes of u, yes? So you feel like somebody's swindling somebody in that, but all of negative 2x dx is equal to du. So now that we're in u land, of course, we proceed as is usual, change the radical to a power. I tell my students to take one step just to do the fundamental theorem, that the definite integral from here to there of a function with respect to something is the integral from here to there of that. I prefer this to be a prefix operator going from 0 to 5, but I could not find anything in the software I was using to create these slides to write that. So I'm putting it over here, which is more conventional. If you look at that book I keep referring to, Well-Structured Mathematical Logic, it shows the advantage of just having a bunch of unary prefix operators in succession strings. This is a postfix operator. We just do the usual here, and then plug in the top, subtract away what you get when you plug in the bottom, and we get our answer, quod erat inveniendum. I'd like to make a few more comments on the structure here. It is good to say in X land, get all your materials in X land ready to go to U land. Just cross that border in one step. Arguments with customs agents is you have enough stress in your life as it is. Just have all the paperwork, everything you need to cross that border smoothly. Don't leave any X stuff behind, and then smoothly go from U land, well in this case, to X land, except there are no X's since it's a definite integral. After having just graded a bunch of papers, I had papers to be graded and the students were doing weird stuff. They had X's and U's intermingle in the main line of exposition. Being a very diligent math professor, I read those as relative integrals, and if they were equal to the right answer, I'd give them credit. Which only very rarely happened. So when you're doing this, put all your stuff with both X's and U's interacting up here in the context area, and then stay in X land, go straight to U land, and then U land if you need to go back to X land. Just do that. Mr. Chairman, my presentation is ended.
Thank you very much, Dr. Scott. Friends and colleagues, please join me in thanking Dr. Scott for another excellent presentation. And with that, I think we'll bring this presentation to a close, and we will see you again next time. Thank you all very much, and thank you again, Dr. Scott.